So today I'm looking at electronegativity and polarity and drawing some compounds. So I'm looking at carbon dioxide. So how am I going to draw this first of all? Okay, I know that carbon has 4 valence electrons. Each oxygen has 6 valence electrons and there's 2 of them, so that's 12. So altogether, I have 16 electrons that I need to place. I place my carbon in the middle since there's only 1 carbon. My oxygen's to the sides of it. And I'm going to just start by doing what we learned in grade 9 and 10 with our sharing bubbles. So I'm drawing my valence electrons around carbon and around oxygen. Okay, so how we would have drawn this is we can see that there's sharing that's going to occur here, 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 and here. Okay, we can also use the more complicated step-by-step method for drawing covalent compounds, which will work for any compound, but because it's a simple one, it's easy to just draw it like that. So that leaves me with this structure where I have 2 double bonds, and I have 2 lone pairs and 2 lone pairs. Okay, so my central atom is the carbon, and it contains a double bond on either side of it. All right, so now I'm looking at electronegativity. So I want to know what the electronegativity difference is between carbon and oxygen. So if I use my periodic table and I find my carbon and my oxygen, and I look for my electronegativity values, so oxygen has an electronegativity of 3.5, and carbon has electronegativity of 2.5. So that's a difference of 1.0, right? So my delta En equals 1.0. So I look at my scale, and on my scale, between 0.5 and 1.7 is a polar covalent bond. So that means that this bond is polar covalent, this bond is polar covalent, this bond is polar covalent, this bond is polar covalent. So I signify my polar covalent bonds by drawing vectors that point to the more electronegative atom, which is oxygen in this case. All right, so looking at this in 3 dimensions, if I have carbon as my central atom, when I'm looking at my VSEPR table for molecular shapes, okay, the double bonds don't count in VSEPR, so we're just looking at them as just bonds. So to my carbon, there is, just like this here, a XX, there are 2 bonded atoms and no lone pairs on my carbon, which means it's a linear shape. Okay, so that means that in 3 dimensions, my carbon dioxide looks exactly the same as it did in 2 dimensions because it's a flat linear shape and I don't have to worry about the double bonds. I like to draw them in 3 dimensions as well, so I know that they're there, but they don't count for the shape part of it. And then our valence electrons that are left along the peripheral atoms, they don't need to be there in 3 dimensions. So I have this polar covalent bond, this polar covalent bond, this polar covalent bond, this polar covalent bond. So what type of bonding occurs in carbon dioxide? Polar bonding occurs in carbon dioxide. But overall, the whole molecule is actually a non-polar molecule. Okay, and the reason for that is that this polar covalent bond here is equal and opposite to this one, so they cancel each other out. This polar covalent bond is equal and opposite to this one. They cancel each other out. Because when you think about it, you've got charge going this way and an equal and opposite charge going this way. So it's like taking 2 steps to the right and then 2 steps to the left. You've really gone nowhere. If you're used to calculating displacement vectors in physics, this is the same idea. Okay, so because those polar covalent bonds have canceled each other out, the overall molecule is a non-polar molecule. Okay, and that means that it's going to have certain properties that we're going to be learning about tomorrow when we learn about intermolecular forces. So this is a non-polar molecule. Okay, H2O, water, same process. First we draw in 2 dimensions, so we can draw these simple ones just using our grade 9 and 10 method of drawing our valence electrons, showing our sharing bubbles, and then transferring that to bonds. Okay, so there's water in 2 dimensions. When we want to place this in 3 dimensions, we have to use our VSEPR table again. Okay, so we look at our VSEPR table, and oxygen is our central atom. It's the one in the center. It's got 2 bonding pairs and 2 lone pairs surrounding it. Okay, so if we look at that here, so that's here like this, 2 bonding pairs, 2 lone pairs, that's a bent shape. Okay, so in 3 dimensions, there's the bent shape for H2O like so. Okay, so that literally means that there's a bend in here. It's not straight across, there's a bend. Okay, and that's because these valence electrons actually take up a lot of space. Sometimes this is drawn almost like Mickey Mouse ears because those lone pair of electrons take up more space, causing these bonds here to bend. Okay, so once again, I look at my electronegativity values, this time between oxygen and hydrogen. So oxygen is 3.5, hydrogen is 2.1, so that's a difference of 1.4. So my delta En equals 1.4, which again is in this polar covalent region here. Okay, so that means that this is a polar bond and this is a polar bond. So I have two polar bonds in this molecule. So what kind of bonding occurs in water? Polar covalent bonding occurs. Now we have to figure out if the entire molecule is polar or non-polar. So to do that, we see if we have symmetry. Do these cancel each other out? Well, no, they don't, because now they're not equal and opposite, right? They're like this. So if you have two items that are pointing at each other like this, they're not canceling each other out. They're not equal and opposite to each other. If we wanted to show that with vector addition, if you're used to doing that, you could show that you go this way. There's my one vector, that's this one here. And then the other one, adding it tip to tail, goes this way. So that's the same as starting here and ending up here. So overall, I have a bond dipole that looks like that. So overall, this is a polar molecule. Okay, does it have polar bonds? Yes. Is it a polar molecule? Yes. Whereas carbon dioxide, does it have polar bonds? Yes. Is it a polar molecule? No, it's a non-polar molecule. So it's all about the symmetry in 3 dimensions. Okay, so one more really quickly. Ammonia, which is NH3. Okay, so drawing, I know that nitrogen has 5 valence electrons. Oxygen has 1. So here's my sharing, which gets changed into bonds, like so. And I do my delta En, so I look up my nitrogen, which is 3.0, and my hydrogen, which is 2.1. Okay, so now I have a 0.9 delta En. Again, that's polar covalent bonds, 3 of them, but this doesn't do me any good to draw it in 2 dimensions like this because that doesn't help me. I have to transfer it into 3 dimensions to actually look at the shape. So I look at my nitrogen, it's got 3 bonding pairs and 1 lone pair. So 3 bonding pairs and 1 lone pair. So it's a trigonal pyramidal or a trigonal pyramid shape. So I need to draw this in 3 dimensions like a trigonal pyramid. So here's my lone pair. I've got the 1 bond that's behind the plane, the 1 bond that's coming out of the plane, and the 1 bond that's in the plane. So you can look up what that looks like 3-dimensionally if you can't kind of visualize this. So this is like a pyramid in 3 dimensions, and I have my lone pair of electrons taking up more space here. That's at the top of the pyramid. Okay, so now when I draw these vectors in here that symbolize these polar covalent bonds, and I look and see, does it cancel out when I add this plus this plus this? No, it does not. Okay, these don't cancel each other out. So overall, I have a polar molecule. Do I have polar bonds? Yes, I have 3 polar bonds. Is this a polar molecule? Yes. Overall, I have a polar molecule of ammonia.